Okay, so today and tomorrow we're going to talk about the disc slash washer method. I'll probably always call it the washer method. Um, and next week we'll talk about the shell method. Okay. Both these methods are going to be for finding volumes of revolution. Okay. So we are going to take a bounded area and revolve it about an axis or a line, and we're going to get a volume. Okay. So here are two bounded regions. Okay. If I take this and I rotate this region about the x-axis, we get this solid right here. Okay. Looks kind of like a glass or a vase. Okay. If I take this region right here and I rotate it about the y-axis, I get this solid with this hole in the middle, right? Because we're rotating about the y-axis, so wherever there's that gap, we get a hole. Okay. All right. So today is the disc washer method. All right. Consider a region bounded by the graph f of x for our upper boundary and our lower boundary g of x from a to b. Okay. What we're going to do is we're going to take this and we're going to rotate it today over the x-axis. Okay, so what's that going to look like? Okay, if I start rotating this about the x-axis, I'm sorry, yeah. All right, so here are, okay, I've rotated and we have kind of this, I don't know how I want to describe it, kind of like a bowl, right, in the middle, right? Kind of a bowl, okay? All right, so how are we going to find this volume with calculus? Okay, what we are going to do is we're going to take our region and we are going to cut it into infinitely many, infinitely small rectangles. Okay, well, we're kind of getting that idea. What do we use for Riemann sums? We don't do a Riemann sum anymore. We just do a integral. Okay, so this is going for an integral. All right, so we're going to break these up into rectangles with thickness dx. Okay, and what we're going to do with these rectangles is we are going to rotate them around whatever axis, and then we take a rectangle and we rotate it about an axis, we're going to get a circular disc or a washer. Okay. So here's my region broken up into all these rectangles. As we rotate these around, we are getting either discs or washers. Okay, discs if there's no hole in the middle, washers if there is. Okay, and we'll talk about when we're going to have a hole and when we're not. Okay, so what we need to be able to do is find the volume of all of these washers and add them together. Right? This sounds an awful lot like a Riemann sum, doesn't it? Okay. So, if I have a bunch of washers, how will we find the volume of each of these washers? So first let's talk about just a disk. How do we find the volume of a disk? You can think of it like that, yes. pi r squared h, right? All right, let's see if this is going to let me write. Okay. All right. That is the volume of a disk. Now, what if we have a washer? Okay, we're going to have to take the volume of the disk and subtract out the volume of the hole, the disk in the middle, correct? Okay, so to find the volume of our washer, we're going to take pi r squared h and subtract pi r squared h, right? And so you'll see what I've done here is I have factored out the pi and the h, and I've just rewritten it like this. Everyone see my algebra in here? Okay. Okay. What you need to remember to be able to do this method is pi r squared h. If you can remember pi r squared h, you can do the disk washer method. Okay? So we haven't even gotten to the calculus yet, but I want you to remember pi r squared h. Okay? So let's talk about this and how it relates to the calculus portion of what we're going to do. Okay? So if the volume of a washer is pi r squared h minus pi r squared h, let's talk about the volume of all of my infinitely small washers, okay? Infinitely thin washers, right? All of these washers have thickness dx, correct? Well, if we talk about the volume of a disk, that height, that is just like the thickness of our disk, correct? So instead of writing h, I'm going to write delta x, because that's our infinitely thin washer. That's how thick all of these are, right? And then instead of r squared minus r squared, I have written function squared minus function squared, y. Okay. Let's look at our picture. This function right here was f of x, right? And this function right here was g of x, okay? So if we think about rotating this piece of area, our outer radius is from the taller function to the x-axis, right? Our inner radius would be our smaller function to the x-axis, okay? So that rectangle that you are going to draw is going to help you determine what your outer radius and inner radius are, okay? All right, so now what we're going to do with this, okay, so this is the volume of one individual washer, right? But we want the volume of our entire surface of revolution. So what are we going to have to do with all of these disks? We're going to have to add them all up. So we're going to have to take the sum of all of our infinitely many disks. Okay? Okay. Now, I have an infinite number of disks that I'm summing up, right? Now, that's basically a Riemann sum. Okay, we did Riemann sums, and then I taught you how to do what?
Shortcuts. Integrate.
Integrals, right? A Riemann sum gave us the integral, right? So, what we're going to have to do, instead of taking the limit of the sum, okay, the limit of the sum is just going to be the integral. Okay? So our washer method, pi r squared h. Okay. Our h is our dx. Our radius, okay, radius squared minus radius squared, okay. Our integral is going to go from a to b, okay. Our limits of integration are just going to, it's going to be much like our area limits of integration, okay. Where are our boundaries? But as long as you can remember pi r squared h, you're going to be fine. Okay, you ready to use an example?
Sure.
Okay. Before we do examples, what am I going to make you do for every single problem? Okay. You better draw a picture of your bounded area. You better have a rectangle, and then we're also going to kind of draw somewhat of a picture of whatever rotation we have. Okay. So here we go. Find the volume when the region bounded by x is 0, y is x, y equals x minus 1, the quantity squared plus 1, is revolved about the x-axis. Okay, so first of all, we need a good picture. Okay. X equals 0 is the y-axis. Y equals x. Is this line right here, right? Y equals x minus 1, the quantity squared plus 1. That is a parabola shifted right 1 and up 1. Okay. So if I'm talking about x equals 0, y equals x, and our parabola, then we're talking about this, it's not a triangle, but it's triangle-ish shaped region right here, right? So I'm going to go ahead and I'm going to erase the rest of this so it's not cluttering up our picture. So there is our region, okay? And what we are going to do is we are going to rotate it about the x-axis. So what we're going to get is something like this. Okay. Did I draw that right? Okay. So now what we're going to do is we're going to draw our rectangle for our discs. Okay. So here is our rectangle, so that when I rotate this about the x-axis, we're going to get a big washer, right? And since we have thickness dx, we know we're integrating with respect to x. Okay, I know that's all we know right now, but I want to reiterate that when we have multiple ways of finding this volume. Okay. So first of all, what are our boundaries for our region? We're going to begin at 0, and then those two intersected at 1. Okay. Volume of a disk is pi r squared h. We're going to have a hole in the middle here, aren't we? So we're going to have washers. So we need pi r squared h minus pi r squared h. So I'm going to write my pi. Our h is just our thickness dx. Okay? So now we need our radius squared minus our radius squared. Okay? Our big radius would be from, I'm going to highlight it in red, right, the top of our rectangle to our axis. How far is that? How far is it from this red curve, the top of our rectangle, to the x-axis? Yes, it's the function. So that's our radius squared minus our inner radius. Where does the bottom of our rectangle sit? Well, it sits on this line, x. So there's our inner radius squared. And that represents our volume. Now, here is where we kind of get to the point where I'm not as concerned with the integration. So a problem like this, okay, let's talk about how we would integrate it. What are you going to have to do first? You're going to have to go ahead and multiply this out, x minus 1 times x minus 1, okay, add the 1. Then you're going to have to square that, okay, and then subtract from it. So there's a lot of algebra going on with this integral right now, isn't there?
Yep.
Okay, this is probably one that I would say either set up and don't evaluate or use your calculator, because I'm not going to get caught up on all of that algebra going on, okay? Do you know how to do it? Yes. Okay, but we're not going to worry about it today. This one today. What I'd like you to do is get your calculator out and go ahead and put this integral in without the pi. Okay, so make that fraction. Math fraction. 23/15 pi. And that's our volume. Okay? So that bowl-shaped figure. All right, let's do another one. Any questions? Okay. Don't worry if your pictures are not perfect.
Well, I mean, as long as they're like visible, yeah. Okay.
Right. What I definitely need is the region with a rectangle, and then if you just very lightly kind of draw, you know, what I would do is just like reflect the region and like a little dotted circle to connect them, so at least you know what kind of is happening.
Right.
All right. But I definitely need this with a rectangle.
Okay.
Okay. All right, let's work on another one. Find the volume of a solid formed by the region bounded by y equals square root of x over the interval 1 to 4, about the x-axis. Okay, so when we're talking about these volumes of revolution, they're either going to give you a function or functions and an interval, or you have to figure out where they intersect, and that's your interval. They also have to tell you where you're rotating it about. Okay, so we have our function, we have an interval, and we're rotating it about the x-axis. Okay, so y equals the square root of x. It's a nice easy one, right? And from 1 to 4, looks like this. Right? So here is the region that we are going to rotate about the x-axis. So we kind of get this trophy-looking shape. Right? Now what we're going to do is we're going to take infinitely small rectangles and rotate them so we have lots of discs or washers. Are we going to have any washers in this problem? No, all of these are going to be discs, right? Which makes the problem easier, right? We don't have a hole in the middle, okay? So when we find the volume of this, okay, first of all, our rectangles have thickness dx, so we're integrating with respect to x. So pi r squared h, pi r squared h. Okay. What is our radius? Okay, here our top function is radical x, so radical x squared. Our bottom function is actually just the axis, and so we don't have to subtract out a whole. So here's our radius squared, pi r squared h. We don't have to subtract out another function. Okay. And what does our intervals from 0 to 4, right? What? Oh no. Then I drew my picture wrong, didn't I? Sorry, guys. I got so excited there. Better? There we go. Didn't change anything but the integration, right? Okay, so like Aaron said, we basically have pi integral of x dx. What is the antiderivative of x? So what we have is pi times 1/2 times 4 squared would be minus 1/2 times 1 squared. So 15/2 pi would be our volume. Question? Okay, if there is no hole, then you're going to have discs and you only have one radius. If there is a hole at any point in your revolution, then you will have washers, okay, and you'll need to have 2 different radii. All right, now we're going to step it up a notch, and we're going to rotate about lines that are not the x-axis. Okay, so how is that going to change things? Find the volume of the solid formed by the region about the line y equals 2. So we have x squared and x are our two functions. We want the region bounded by these graphs rotated about y equals 2. Okay, we've worked with this region multiple times by now, haven't we? Y equals x and y equals x squared. Do you agree with my region? It is really small. And I made it really small because we are going to have to rotate it about the line y equals 2. Okay. So I'm just going to draw it really lightly in green here. Okay. So we get this picture, right? We have this. It's going to be kind of a bowl, right, with a slant inside. Okay. All right. So I'm going to draw in my rectangle here. Do you agree that we're going to have washers? Okay, we're going to have washers with thickness or height dx, correct? So now we need to focus on pi r squared h. Here's our pi, here's our h, now we need r squared. We have washers, so we need our outer radius squared minus our inner radius squared. Let's talk about our outer radius. Okay. All right. Since we have a different axis of rotation, it's not necessarily just the height of our rectangle anymore. Okay? Our radius needs to refer back to whatever axis we are rotating about. Okay? So here, my axis of revolution is y equals 2. What function is the furthest away from y is 2? X squared, right? And how far are all of these rectangles from? Okay, well, I wouldn't say plus 1. Okay, what we need is the distance from this line to each of the bottoms of those rectangles. What is the distance from this line to this curve? How do we find that? Top minus bottom. Right? The height of that radius is the top, which is our line, minus our bottom, which is our x squared. Okay? That's the distance right there. Now let's talk about minus our inner radius. Okay? The top of our rectangles to y is 2. What would that distance be? 2 minus x. So that's our inner radius squared. Okay? Okay. Questions? Because I know it's different from our other. Okay, once we have a line that is not the x-axis, our radii are no longer just a function. We have to talk about their distance to our axis of rotation. Okay? Now, what are our limits of integration? 0 to 1. Let's talk about, we have time. We can integrate this one. What would we have to do?
You have to solve or first, so the first one would be x to the fourth minus
This first one we would start with
x to the fourth.
4
Oh,
minus 4x squared and then x to the 4th. Is that okay?
yeah, I just always put the x's up front.
That's fine.
That's why. That's why he said no. We start with 4. Why?
Okay. And then this one would be?
It's the same thing, but the powers are lower. It's just 4 the x on 6. And then if you want to change, you can go plus.
Okay, so let's combine like terms. We have 4 minus 4. We have x to the 4th. What about our x squared?
Negative 3x squared.
And our x's?
No, it's not. No, that's negative 5x squared.
Aaron's not the only one helping me here, right? Then we have plus 4x?
Yes.
Okay. Then, okay, so now we have to actually do our integration. 1/5 x to the 5th minus 5/3 x to the 3rd plus
2x.
evaluated from 0 to 1. Okay? So we have pi times, we plug in 1 and get 1/5 minus 5/3 plus 2. We plug in 0 and get
0.
0. So now you need to add these. We need to get these. Okay, common denominator would be 15, right? So we have 3/15 minus 25/15 plus 30/15.
8/15.
This would be a problem that you could do on a non-calculator part.
I think it's kind of definitely non-calculated part.
What?
Alright.
Okay. I'm just saying the algebra is not ridiculous enough that this would. We also need to be able to kind of realize when the algebra is going to be okay and when it is going to be gross. Our first example, the algebra is really gross, isn't it? We have to square this binomial, and then we're going to have a trinomial that we're going to have to square. That's gross. Okay? Once we have multiple methods, it's going to be important to recognize when things are going to be nice to integrate, when things are not. Okay? All right, we're going to do one more example. Yes.
Will we ever rotate anything about a line that isn't straight horizontal or straight vertical?
It's impossible.
We will. Okay. Tomorrow we're going to rotate around vertical lines. Today we're just going to focus around horizontal lines.
Oh wait, that's not possible. I thought you meant a curved line.
No, just like any like
Like y equals
yeah,
x.
like y equals x.
Okay. So this region, we're talking about y equals 4 is a boundary. X equals 0 is a boundary. And 1/2 x squared. So let's
So we have
see.
1, 1/2, 2, 2, 3, 4.5.
And 4, 4.
Sure.
Yes or no question?
Yes.
Okay.
Sorry, I didn't know we were going to before. I was just.
Right, because we have y equals 4, so we need that intersection point there at 4, 4. Right?
Oh, okay.
So what we're going to do is we're going to rotate this around y equals -2.
Would that be 4, 4?
What?
It wouldn't be 4, 4. It'd be 4, 8.
Oh, whoops.
Because it would be 3, 4.5.
Yeah.
So what's, okay. What's our intersection point then?
It'd be between 2 and 3.
Use algebra. Let's use algebra to find it. What is that intersection point? When does 1/2 x squared equal 4? When x squared is
8.
8. So this is radical 8. Okay. So now we're going to rotate this around y equals 2. Okay. So that's what's happening, right? Disc or washers. We're going to get these washers, right? If I draw my rectangle in, we're going to rotate these around, and we're going to have big donuts, right? The big hole in the middle. Okay. All right. Now we need to talk about how to actually find the volume. All right. We know pi r squared h. Okay, right? The height of all of these washers is dx. Okay, let's talk about our radius. Now we have washers, so we need radius squared minus radius squared. Let's talk about our biggest radius. Our biggest radius goes from where to where?
Y equals 4 to y equals -2.
okay, our biggest radius, okay, if I look at these rectangles, the top of our rectangle is the furthest away. So how far is it from y equals 4 to y equals negative 2?
6.
6. So our outer radius is always 6. Okay? So 6 squared is our outer radius minus, let's talk about our inner radius. The bottom of our rectangle to our axis of rotation.
X squared plus 2.
Okay. I got two different answers shouted out. Remember, we always have to say top minus bottom. So since the rectangle is more positive, it needs to come first. So this function is 1/2 x squared, right? Minus negative 2. Okay, so let's talk about this versus the other one. Okay, here, when we found our radii, we had to take the line minus our function, right? Because our axis of rotation was above our rectangles. Here, our axis of rotation was below our rectangles, so we took our rectangle minus our axis of rotation. Okay, it still has to be top minus bottom.
Can you go back to the other one? Oh, okay. So the blue was the original.
Yes. Okay. If you draw this portion of your picture, draw it really lightly so you know which one was your original area. Okay, and so you know which was, if it's above or below your axis of rotation. Okay, your homework assignment, okay, and this one wouldn't be too bad for non-calculator, but to save time, I'm not going to have you punch it in. I want to give you a few minutes to begin your assignment. All right, now, anything that I put a box around, you are doing without your calculator. Anything that is not boxed, you may put in your calculator and then multiply it by pi.
Say 3 for 13.
Okay. 1, 2, 3, 4. So you have 6 problems without your calculator where you actually have to perform the integration. 1, 2, 3, 4, 5, 6, 7 of them. You can use your calculator for. Okay. Now, if they're nice fractions, then find the volume of revolution and then write, your fraction times pi. If they're not nice fractions when you integrate, then just multiply by the pi and give me the decimal approximation.
Wait, so box means calculator?
No.
Box means calculator?
So what I'd like you to do is go ahead and begin working on this. See if you can set up and integrate number 1, maybe get to number 2 and 3. I don't know.